All right, folks, we're back. And I realized I was getting a little bit sloppy, actually, with my notes. So this is actually, this 5% rule was one that was on your slides. Just going back to the slides. So sorry, these videos are not the best. Okay, so the 5% rule. The one we did for apply the 5% rule for acetic acid, well, we just did that one. So that was number 2. Okay, from the notes. So just keeping with the slides here. Number 3. Okay, again, this is on the slides. I'm not going to copy that whole thing down. It's slide number 8. This is an example of the 5% rule. It says ammonia is a weak base, reacts with water to produce ammonium cations and hydroxide ions. This is actually one of the check your learning problems that's in the book. It's not written exactly this way, but it is one of the check your learning problems. And it's just another 5% rule. So I'm actually going to go through these examples fairly quickly because there's a couple of nuances with how these can be done. It's not always start off with an initial reaction of a product or a concentration of a reactant, gee whiz, and then push it to products. It's not always that left to right rhythm. Just so we don't get used to doing exactly one kind of problem. So I'm going to do this one fairly quickly. There's not much for me to say. So in this case, it's a base, so it's a Kb. And actually, interestingly enough, it has the exact same numerical value as the Ka for acetic acid. So you can probably see where we're going with this. It's the exact same type of problem as acetic acid, just using a base rather than an acid. Okay, so I'm just going to set this up, and you can do it. We can go much, much faster. So there is one little twist in this problem, and this is something that we're going to talk about more in the next chapter. Water, in this one, is actually a reactant, but water is also the solvent. It's part of the medium of the reaction, and we don't typically put those in the K expression. So you got to take my word for it on this one. So when we set up the ICE table, we only use those parts that are in the homogeneous equilibrium. Water, yes, it's a reactant, but we don't include it in the K expression. That'll be something that's a little bit more obvious next chapter and some other ones, just so you don't always write every single chemical every single time into your K expression. So we actually ignore the water in this case. And the initial concentration of ammonia is 0.25. So it's a lot less than the acetic acid, which was 1. So the 5% rule might not apply here because when we check the 5% rule, this is going to be a lot smaller, but we still have to check it. And these are 0. This has to go down. Those both have to go up. Go right to the K expression. So Kb is going to be this times this divided by that. So 1.8 times 10 to the minus 5. It's just a coincidence that it's the same number. Equals x squared over 0.25 minus x. Again, this is how we set up the Kb expression equals equilibrium times equilibrium divided by equilibrium. And let's assume that we can ignore that. It's not 0, it's negligible. And I'm going to let you solve that. Bring this concentration over here, multiply it, take the square root. So K times initial concentration, square root should give you x equals 2.1 times 10 to the minus third, and that's always a molarity. That's 10 to the negative third. And let's check it. Does the 5% rule apply? So 2.1 times 10 to the minus third molarity divided by the initial times 100. and you get 0.84%. Again, not 8.4%, 0.84%, and that's a lot less than 5. So that works. So to answer this problem, again, look at the check your learning problem if you don't get it. The equilibrium concentration for ammonium would be 2.1 times 10 to the minus third. The equilibrium concentration of hydroxide would be 2.1 times 10 to the minus third. And lo and behold, when you subtract these two, well, the equilibrium concentration of ammonia is pretty much the exact same thing as it started because of sig figs. The sig figs don't work here, so this x ends up being negligible, which is kind of the point. Which just looks kind of strange that it's the same number that it started with. It didn't go down at all. Well, that's because the k is so small. Okay, so that's example number 3. I'm going to do example number 4 now. We're on slide 9. So if you want to copy down number 4 while I get organized here, go ahead and do that, because I'm making some subtle changes. In this one, there's a heterogeneous equilibrium, so we actually ignore something completely, kind of like this one. And you're not given a reactant, you're given a product, and you're also not given a molarity, you're given a moles and a volume, but that's easy. You can calculate a molarity, moles over liters. That's just a small twist. Okay, so, and it's a pretty small equilibrium constant. Okay, anyway, copy all that down and see if you can write the chemical equation that I'm about to do. And let's see if we can do this one. So this is number, that's number 3. I'm going to erase that because I need the space. That's fine. So we're taking what? Solid, that should be a giveaway. Solid ammonium. Oh, I'm not even sure what to call that. I'm not exactly sure what the chemical name of that is. That's terrible. I think this may be another example from the book. So we're taking a solid. So don't forget that. We are not going to put that in the K expression. It's heterogeneous. The homogeneous part are the two gases that are given off. Ammonia gas and dihydrogen sulfide gas. Those are the homogeneous parts. That is not them. Don't put that in there. Easy enough. Just like water over there. We ignore it. It's a solid. And I'm going to leave you to do it. It's 0.2 moles and it's 2 liters. The initial concentration here is 0.100. Molarity, they're all molarities. I'm not going to write the units. Okay, well that's kind of weird. So we have a reaction where we have this solid, there's already some ammonia lying around, but there's none of this. The problem doesn't say there's any dihydrogen sulfide around at the initial stage. Yeah, okay. Well, that's kind of weird. So what's our x have to be? We don't even, normally we would just want to go minus x, but we don't start with anything here. Which direction does this reaction have to go? It has to go that direction. We have to produce some H2S, so this has to go up by some amount. What does that mean? That means some of this has to decompose to make it. But if that's going to go up, this has to go up too. That's a strange thing. We're taking an initial concentration, we're adding something to it. It's just a small twist so you don't get locked into doing the exact same problem every single time. Okay? So you have to think about the chemistry, not just the algorithm of the math. So this is going to be, the equilibrium is going to be 0.100 plus x, and then plus x. Now we're home free. We're given an equilibrium constant. Remember, this is a heterogeneous equilibrium. equilibrium, so we don't put that there. So Kc in this case, oh, this is balanced, right? There's no squares or anything, which makes this easy. The Kc is going to be the ammonia concentration times the H2S concentration. Nothing in the denominator, because that's probably gets old me saying that. It's heterogeneous, so we don't do that. So in this case, we give the given value 1.6 times 10 to the minus 4 is, oh sorry, equals 0.100 minus x times x. So that's the math setup. We do that, we set this up. Does the 5% rule apply? Well, how are we going to do that? Well, that means, okay, well that means I'm going to assume that x is small compared to the initial concentration. We have to keep that one there. We can't ignore that. That wouldn't make any sense. So we're going to ignore this one. We're going to assume that x is negligible to this. We can't ignore it here. So this math actually turns out to be, well, if it works, 1.6 times 10 to the minus 4 equals, geez, I keep doing that, 0.100 times x. That's really simple math. X equals 1.6 times 10 to the minus 3. That's math you can probably do in your head. Just bring that over here. Does the 5% rule apply? Well, 1.6 times 10 to the minus third over the initial concentration, 0.100. These are molarities, times 100 equals 1.6%. Well, that's less than 5. Again, 5% is just a rule of thumb. It's like, okay, fine. So again, what would the answer to this problem be? The answer to this problem would be the equilibrium concentration of hydrogen sulfide would be, dihydrogen sulfide would be 1.6 times 10 to the minus third molar, and the equilibrium concentration of ammonia would be 0.102 molar, because actually when you add this plus x, you'll get 0.102 molar. So we'll add to it some. Okay, so that's another 5% rule problem. I've got a lot of these, I don't know why I have so many. Actually, that may be it. Okay. I think that's the last one I'm going to do for this one, so it's a really short video. That's the 5% rule. Okay, where we're headed next, that was a pretty short video, which is totally fine. So you want to be able to set up the 5% rule. There are some homework problems in problem set 3. Oh yeah, there's some really good problems in here. You may want to actually, after this video, start looking for 5% rule problems you can do. Not all of these can be done with a 5% rule. There's one last thing I need to show you, and that's actually not in your book. So what happens if we have a large equilibrium constant? What if it's a huge equilibrium constant and you're given an initial concentration of a reactant? It wouldn't make any sense at all to assume that x is small. 0 sense. The last video I'm going to show you again, which is not part of the book, is we're going to take the equilibrium, if it's a big equilibrium constant, and push it to one side, push it to the other side, and then bring it back to make x small. That may not make any sense, but I'm going to show you a couple examples. There's one in your homework, and that may also be something that we have to set up office hours for to go through later in this particular week, which is fine. Okay, so that's the 5% rule. Excuse me. The last video is called Pushing Equilibria, and that we'll get to that one a little later.